So today we're going to talk about shapes, angles, and lines. In particular, we're going to talk about parallel shapes and the angles that make them up, and the lines that identify how they're parallel. So let me go ahead and get this started. So first we're going to go over these shapes right here. The isosceles trapezium, or the isosceles trapezoid as it's commonly known here in America. The parallelogram, the kite, the rhombus, the rectangle, and the square. So the main difference between the square and all of these is the square has 4 equal lines and 4 equal angles. Talk about that in a second. So here you can see the square has all 4 equal lines, and we can identify these lines as being parallel by using hash marks like this. Just like that. That shows that all these lines are equal, and we can see that all the angles are right, which means all these angles are equal. So this figure is completely parallel. Here we have the rectangle. So the rectangle is a little different than the square. All 4 angles are equal, but the sides, 2 sides are longer, and the 2 sides are shorter. But these sides are parallel, and these sides are parallel. The rhombus, so all 4 sides are equal. The lines are parallel, but the angles are not equal. Here you can see has 2 acute angles and 2 obtuse angles. So even though this figure is parallel, it still has uneven angles. Here we have the kite. We can identify the lines as being parallel based off the hash marks right here. These angles are equal as well. It's 2 equal angles right here. It can be split in half evenly, so this figure is also parallel as well. And here we have the common parallelogram. This is what everyone thinks of when they think of parallel figures. So you can see right here, it's not quite a square just based off of how it's done, but the lines are equal here and they're equal here. All the angles are going to be a little bit different. So these angles are going to be smaller than these angles right here, which means this figure, although it is parallel, the angles are not the same all the way around. But all the lines are, however, equal. And lastly, we have the isosceles trapezoid. These 2 angles are equal, and these 2 sides are equal. That makes this figure a parallel figure. So here we have the triangles that we're going to go over. We can put them into 2 different categories. You can categorize them by side or by angle. So the acute triangle has 3 angles that are all less than 90. The right triangle has 1 angle that's 90, and the other 2 angles add up to 90 degrees. The obtuse triangle has 1 angle that's greater than 90, and the other angles that are less than 90. The equilateral triangle, these are identified by side. All 4 sides are equal. You can see just by the hash marks that all 3 sides. Triangles have 3 sides. All 3 sides are equal. You can tell based off of the hash marks. The isosceles triangle has 2 equal sides and 1 longer side. The scalene triangle, none of the sides are equal. And lastly, we're going to watch a video. Although it's not based on the figures that we're doing, I feel it's important to watch because it shows how geometry is used in everyday life and some of the hobbies that we really enjoy. And that includes football. So it is important to see how the aspects of geometry are used. We'll watch the video on this, and then we'll have a final discussion after. Let's hope it starts. Oh, all right. Let me turn up the volume just a bit.
Whether throwing a screen or launching a bomb, NFL quarterbacks are spin doctors. Firing fast spirals that cut through the air with pinpoint accuracy.
The shape of the football is unique and allows you to be able to throw the distances that you can.
Former NFL quarterback Joey Harrington says the secret to throwing the perfect spiral starts with his fingertips.
I like it this way because it helps me get a little more rotation on it. It helps me get a little more spin.
The spiral is what tends to keep it going along the path that the quarterback would like.
Professor Tony Schmitz is a mechanical and aerospace engineer at the University of Florida and coach of the Newberry High School football team. Around campus, he's known as the Pigskin Professor.
My enjoyment for football started when I was very young.
Schmitz says the key to throwing a tight spiral comes from a football's unique shape, which is different from the ball used in most other sports like tennis, baseball, and basketball.
Most sports use a round ball or a sphere because it's symmetric. No matter where I hit it, no matter where it bounces, it will have the same response.
While spherical balls come from the two-dimensional shape, balls are formed from a two-dimensional shape called an ellipse. An ellipse can then be divided by its two axes, its long or major axis and its minor axis.
From the two-dimensional shape of an ellipse for a football, if we were to rotate that about its long axis from one end to the other, we end up with a prolate spheroid.
A prolate spheroid, this clumsy word may explain some of the mad dashes seen after a fumble. What makes a football unpredictable on the ground is also what makes it travel through the air so smoothly and accurately.
It is very surprising how accurate they are, but you realize how much work goes into it.
Unlike a spherical ball, the prolate spheroid shape actually helps the ball to spiral through something called the gyroscopic effect, which helps maintain its control and trajectory by its continual spin.
We can think about the gyroscopic effect of the spiral as being a stiffening effect on its path. It tends to keep it on that path.
A spiraling football is also effective at moving through the air because it reduces the amount of drag or air friction against the ball. As the football spirals, the air on the surface of the ball is broken up, allowing for less drag and a smoother trajectory.
That rotating motion tends to break up that boundary layer between the fixed air and the football surface, which reduces drag.
But if a football is thrown a little off, it begins to wobble. Pass encounters more drag and does not benefit from a gyroscopic stiffening of its trajectory.
If I've got a ball that's kind of wobbling like this, it creates more surface area for the wind to hit it.
So, the tighter the quarterback spiral, the less air resistance on the ball, allowing it to travel farther.
Without the spiral, it would be very difficult to keep the football on a path.
It becomes a thing of perfection, and quarterbacks love to be perfectionists.
Perfection that only a prolate spheroid can provide.
All right, so here we can see how the actual application of geometry is done in football. The way the ball is thrown, it creates a spiral and it makes it easier to fly through the air. So properties like this can be applied to other shapes as well, like how the square, how the rectangle, how they're all used in everyday life. When we look around, we can see the room we're in right now. It's cubical, but it's square in nature. The walls, they're all angled. Everything has a geometric shape to it, which is why this is important, which is why I actually showed you this video. Geometry, it applies to everyday life. So that will be the lesson today, and thank you for watching. I'm glad you're here today.